The two structures that we're going to spend a little bit more time on are the crystalline solid that carbon forms. Carbon actually forms a couple of different crystalline solids. We're going to focus on diamond and on graphite. Diamond is a tetrahedral structure. All the bonds between the carbon atoms are covalent. That makes it very strong. So each carbon is tetrahedrally bonded to others. Graphite is a little bit different. Graphite, the carbons form hexagonal rings. In the layers, I have covalent bonds. So these are all covalent bonds. So I get a 6-carbon ring. It turns out, though, that I have some double bonding going on. So I have pi bonds between the rings. Pi bonds, remember, are formed from delocalized electrons. Okay, what this does for graphite is within each layer, the graphite crystal is very strong. But between the layers, they're not attached very strongly. And what this allows the layers of graphite to do is slide. Because they can slide, this allows graphite to serve very nicely as a lubricant, allows things to slide back and forth. So when you don't want to use oil or something messy like that, you can use graphite powder and it acts very nicely as a lubricant. When you use a pencil, what you're doing essentially is peeling layers of graphite mixed with clay off of the solid and leaving it behind on your paper. So the fact that you can peel layers of graphite off allows it to be used as a writing utensil. Because it can slide and is flexible in a linear fashion or a planar fashion, graphite has been used in things like hockey sticks, golf clubs, bike frames, where you want it to be able to flex, but you don't want it to be able to break, and you also want some strength along that line as well. So graphite's got a lot of uses. The other thing is, because it has delocalized electrons, graphite can conduct electricity. With those pi bonds, it has delocalized electrons. Just like metals and their delocalized electrons, it can conduct electricity. Okay, semiconductors we're going to fly through. Semiconductors generally start with either silicon or germanium. You want to start out with very pure silicon or germanium, and it turns out plain old silicon, plain old germanium are lousy conductors. They are essentially network crystals, just like carbon, and they don't conduct electricity. We take a look at the structure right above here, and we've got electrons, they're held in covalent bonds. So those are all my silicon atoms. So how does it form a semiconductor? Semiconductor means that it is a substance that will conduct electricity, not heat so much, but electricity under certain conditions. So we're going to stress it, and we're going to add some impurities. These really aren't impurities, these are specific elements that we want to add in specific ways, and that is called doping. And the elements that we tend to use when we're doping to make our semiconductor are arsenic or gallium. The reason we dope with arsenic is it has 3 p electrons. Gallium has 1 p electron. That's 1 more than silicon has in the case of arsenic. That's 1 less than silicon has in the case of gallium. So what that does is that either gives us an extra electron or it gives us an electron hole. So if we take a look at this diagram here, if we dope with arsenic, as that highlighted particle shows, I have 5 electrons instead of 4. So that means that 1 electron is not involved in a bond, and it can actually move around and take the place of other electrons. It's essentially a free floating electron because it's free and moving around, and if we put a series of gallium atoms, arsenic atoms, so if we put one here and we put one here, what we have is an extra electron here to here to here, and so we can create a path for electrons to flow through this crystal that are very specific. And so that's how these microcircuits that go into your iPod and your phone and all this cool stuff are made by semiconductors. If we put gallium in, then we have a hole. We're missing an electron here, and so it wants an electron from someplace. It's going to try and pull it. And what these two types of semiconductors do is they tend to make sandwiches of N-type, which has the extra electron, and P-type, which has the missing electron, P for positive, N for negative. And what that does is that essentially is like a pump that pulls electrons through the crystal in a specific path and allows a current to flow through very small space in a very specific way. What the animation is showing is we start out with an electron, extra electron, moving through, and the bonding electron kind of bounces around and creates holes somewhere else, and so that electron only follows a specific path within the crystal, and that's where the current would flow.